In this video we're going to discuss the coproduct topology, which is the first of three constructions that we'll discuss, which allow us to construct new topological spaces from ones that we know about already. So we're going to let Y and Z be topological spaces, and for simplicity we're going to assume that they're disjoint. Okay, so then we can form their union, Y union Z, and we'll introduce a topology on that. Okay, so for U, a subset of Y union Z, we declare U be open if U intersect Y is open in Y, and V intersect Z, so U intersect Z is open in Z. Of course, U is going to be, because U is the union of, because we're looking at Y union Z and Y and Z don't overlap, that means that U is just a union of the part that lies in Y and the part that lies in Z. So this means that U is equal to V union W, with V being the part in Y and W being the part that's in Z. Okay, so that's what we're going to mean by saying that a subset of Y union Z is open, and the claim has got to be that this gives us a topology. And we're going to call this topology the coproduct topology, once we've justified that it really is a topology. So what do we have to prove? Well, firstly, we should prove that the empty set and the whole space are both open. Well, the empty set is the empty set union the empty set. Okay, so the empty set's open in Y, the empty set's open in Z, the union of the empty set and the empty set's the empty set. And Y union Z, well, that's Y union Z, with this being open in Y and this being open in Z. Okay, so this from this we see that the empty set and Y union Z are both open, which is the first of our axioms for a topology. Now for the next axiom, so suppose we have a family of open sets in the space of Y union Z. So then the UI is going to have the form VI union WI, with VI open in Y and WI open in Z. Because, we're assuming that UI is open in Y union Z, and this was the definition of what that means, that UI can be written as the union of an open subset of Y and an open subset of Z. So now if I just take the union of all these UIs, well, on the one hand, that's the union of the VIs, union with the union of all the WIs, and this one is open in Y by the topology axioms for Y, and this one is open in Z by the topology axioms for Z. So that's so that union is going to be open in Y union Z. And finally, suppose U1 up to UN, so I've got some finite list of open sets. So again, you're going to have UI is VI union WI, is VI open in Y, WI open in Z, and then it's not hard to see that the intersection is just going to be equal to you take the intersection of all the V's, union the intersection of all the W's, this part being open in Y, and this one open in Z. Again, we're using the topology axioms for Y. Topology axioms for Y say that the intersection of finitely many open subsets of Y is still open in Y, and similarly for Z. So this tells us that this intersection is open in Y union Z, which is the third axiom for a topology, and that proves that we've got a topology on Y union Z, as I said, and that's called the coproduct topology. Okay, so here's a few observations about the coproduct topology. Okay, so Y is open in Y union Z because it can be written as Y is open in Y and empty set's open in Z, so the union of those is empty in Y union Z. Similarly for Z. And the next observation, well, so Y is open, so the complement of Y is closed. What's the complement of Y is just Z. And Z's open, the complement means that the complement of Z is closed, but the complement of Z is just Y. So Y and Z, they're both open in Y and Z, but they're also both closed. It's not a super common thing to happen for a set to be both open and closed, but it is perfectly possible. And you can just see a little example of this sort of thing, right? I mean, if we take space like this, the interval from 0 to 1 and interval from 2 to 3, you see here, let's call this space X, and then 0, 1 is the same thing as minus 0.1, 1.1 intersected with X. That's both open and closed in X, right? Because it's closed because it's just a closed interval in the whole real line, and then it's also the intersection of this open set here with X, so it's open in the subspace topology. So the left-hand interval is both open and closed. The right-hand interval is also both open and closed. This is that's the kind of thing that can happen. And then we can regard Y as a subspace of Y union Z. So it inherits a subspace topology. So in principle, we might have two different topologies on Y. We start with a topology on Y and a topology on Z. We combine them to make the coproduct topology on Y union Z, and then we restrict that down to get the subspace topology on Y. That's in principle a different topology on Y, but it's a basic lemma. This is the same as the original and of course it's the same symmetrically for Z. Okay, I think I'm not going to write the proof of that. The proof's in the notes, or you could just take it as an exercise. Then, and so Y is an open subspace and Z is an open subspace. They get the same. They get the original topology as the subspace topology. The next thing I want to talk about is about maps out of this Y union Z. This is a kind of basic thing from the perspective of category theory. We've been talking a little bit about categories, and the category theory perspective encourages us whenever we construct a new object, we ought to be thinking about how we can characterize the morphisms to that object or the morphisms from that object. Okay, so that's what we're going to do here. Let's just consider this in terms of sets for the first instance. If Y and Z are just disjoint sets, and T is another set, then to define a function, f from Y union Z to T, we need to just define the restrictions. G is going to be f restricted to Y, so that's a function from Y to T, and H is f restricted to Z, that's a function from Z to T. And this is kind of a one-to-one correspondence. We can we've got any pair of maps, G from Y to T, H from Z to T, then we can just combine them to get a map from Y union Z to T. So we can say this bijection sets Y union Z to T. Okay, this is the set of all functions, the set of morphisms in the category of sets from Y union Z to T, or in other words, just functions. That's in bijection with this product here. So a function f from Y union Z to T just corresponds to a pair of functions G and H, where G goes from Y to T and H goes from Z to T. We're going to say, now suppose that Y, Z, T are all topological spaces. And then we're going to claim that F is continuous with respect to the coproduct topology. If and only if G and H are both continuous. So that means that the set top Y union Z to T of continuous maps from Y union Z to T, that bijects with pairs top YT across top ZT. So a continuous map from Y union Z to T just corresponds to a pair of continuous maps, one from Y to T, one from Z to T. The proof was basically suppose we've got an open subset T of A of T, then F inverse of A, well, that's just equal to G inverse of A union H inverse of A. This is being the part in Y, and this is the part in Z. So that means that F inverse A is open if and only if G inverse A is open in Y, and H inverse A is open in Z. And once we've observed that, then the claim's kind of clear, right? The F is continuous if and only if every such pre-image is open, and G is continuous if and only if every G inverse A is open. H is continuous if and only if every H inverse A is open, and so it all fits together.